Okay, so the answer to question 1. We'll do it with our standard methodology. What have we got? So we have an object in a circular orbit. Or in other words, we have an object undergoing uniform circular motion. So we know that in this case, we have two forces. We have the force due to gravity, and we have the centripetal force. And we know because we're in a circular orbit, then those two forces must be equal. So we just substitute in our equations and rearrange and solve. And we find that our circular orbital speed is equal to the square root of gm on r. So our circular orbital speed depends only on the mass of the large object, of the object that we're orbiting around, and the distance r that we are from that object, so the orbital radius. The second question is to find the total energy of an object in orbit. So, what do we have? Well, we know that the object is in a gravitational potential field, so it has a gravitational potential energy, and we know the formula for that. We know it has a velocity, keeping it up in orbit. So we know it has a kinetic energy equal to half mv squared. And we know from our previous question that the formula for that velocity is v squared is equal to gm1r. We're told that the only force acting is gravity, and we know gravity is a conservative force. So that means then that we know that the total energy of the object is simply equal to the mechanical energy, which is equal to kinetic plus potential energy. So again, if we then substitute in our equations for the kinetic and potential energy, and then we can substitute into our kinetic energy our formula for v squared, we find that the total energy of our object in orbit is equal to minus a half gmm on r, which if you look closely we can see is actually equal to the negative of the kinetic energy.